Convidamos nesse momento para fazer a sua apresentação a Keynote Speaker, professora doutora em Estatística e Genética Animal e mestre em Estatística, ambas pela Universidade de Iowa, nos Estados Unidos, a professora Alicia Carriquiry. Uma salva de palmas, senhoras e senhores.
Okay. Oops. Yeah. Good day, everybody. I am very, very happy to be here. I'm from Uruguay. Little glitch. So thank you very much for inviting me to speak here. I have been in Brazil many times, but never in Curitiba. And it's a really lovely city. I like it very much. I would like to thank Paulo Akira in particular because I think he's the one that made my invitation possible, and I'm very, oh, there he is, and I'm very grateful. So I'll talk, Didier introduced the issue of standards, and I am going to get a little bit into the weed and talk about the new research and where forensic science is going. I am the director of a center called CSAFE, which is the Center for Statistics and Applications in Forensic Evidence. And we do a lot of work in trying to develop the statistical framework, machine learning methods to evaluate evidence. Our focus is on pattern comparison disciplines like firearms, latent prints, and these other type of disciplines, but we work in other areas as well. So this is the context. Forensic scientists are asked many different types of questions. I am going to be focusing here on the question of source. So there's a crime scene, there's some item at the crime scene, maybe it's a biological stain, maybe it's a fired bullet, and you have a suspect, you recover an item from the suspect, perhaps a test shot from the suspect's gun, and you ask, thank you, obrigado. You ask whether that gun may have fired the bullet at the crime scene or whether the suspect's finger was the one that produced the latent print, and that's the type of questions that we try to answer. These are not easy questions to answer. So the idea here is that what we try to move away from the traditional reporting of examination results. So the forensic scientists sometimes are put in an impossible position in the sense that they are expected to issue a categorical conclusion. This is an identification or this is an exclusion, and this is all fine and dandy if those opinions are correct. But, in a sense, examiners ought to be allowed to recognize uncertainty. Everything is accompanied by some uncertainty. And so we're trying to move from this categorical reporting to a reporting that admits the possibility that I am not 100% sure. There is no such thing as 100% certainty anywhere. And so how can we move from this categorical framework to a more probabilistic framework that allows you to say what you really believe, right? Yeah, this looks pretty similar, but you know, there's a little room for error here. And so that's where we're gonna go. And so this is the outline for the rest of the talk. I'm going to think like a scientist, formalize the question of source, talk a little bit about likelihood ratios, how you calculate it, how you interpret the results, and then I'll give some examples. I'll talk a little bit about the evaluation of handwriting, the evaluation of bullets, and if I have time, I'll talk a little bit about chemistry, so chemometrics. All right, so let's revisit the question of source. So you have a crime scene, you find some sort of a pattern, and a pattern could be a shoe print, or it could be a handwritten document, or it could be a fired bullet, any number of things. And typically, these patterns can be represented by an image of some sort, right? You take a photo, or you take you collect the fingerprint. And so what we have in terms of data, if you will, are these images. And the question is, can you place the defendant at the scene of the crime? And let's think about so what I'm going to do here is think in terms of what are the possible scenarios. So we can think about two scenarios. One is that the defendant is actually the source of the trace you find at the crime scene. The other one is that somebody else may be the source. And so these are what's called the propositions. Sometimes you will see them listed as HP and HD, where the P stands for prosecution, the D stands for defense, or sometimes it is HS and HD for same source, different source. It's all the same story. And so the question we ask ourselves is, we have some evidence, and does the evidence support the first proposition or the second proposition? So that's where we're trying to go. And so what is the state of the art? So the state of the art, let me just start from the beginning, except in forensic DNA analysis, everything that I'm going to be talking about today has not really been implemented. So the state of the art in terms of pattern comparison disciplines is examiners get the evidence. For example, they may get the fired bullet from the crime scene, they may get a test fire from the suspect's gun, and they visually compare the striations, for example, on these bullets, perhaps with the aid of some instruments like a comparison microscope, and then they report their findings or their observations in the form of categorical opinions. In the case of firearm examiners, they might say, this is an identification, or this is an exclusion, or this is an inconclusive. And there's different flavors of inconclusives, inconclusive A, B, and C. And so the question is, how good are examiners at doing this type of analysis and reporting these findings? Well, it's very difficult to say. This is a study that was done, it's called the AIMS-2 study. This was on firearms, and there were two big parts. It was a very large study funded by the FBI. Examiners, the participants were asked to, they were sent kits, and a kit consisted, for example, of 3 bullets that were known to be fired from the same gun, and a question bullet, and they were asked, was the question bullet also fired from the same gun? So essentially, does the question bullet match the other 3 bullets? And they also had to, there was another part that did cartridge cases, breech face markings on cartridge cases. And there, for example, you have that among the mated pairs, there were 14,000 mated pairs. There were only 41 exclusions, so those are false negatives. There were 288 inconclusives, and the vast majority of the mated pairs were correctly classified as identifications. When you look at the non-mated pairs, however, look what happened. Only 961 out of the almost 3,000 were correctly classified as exclusions. The vast majority were considered inconclusive, so no conclusion essentially, and there were just a few false positives. False positives, of course, is what you worry most about. And not only in this particular black box study, but in general, inconclusives are counted as correct. So if you count the inconclusives as the correct decision, then you find that the false positive rate is very, very low. It's just 20 divided by 2,842, and that gives you less than 1%. But some inconclusives may not be correct decisions. Maybe they should have concluded something else. In fact, 87% of those inconclusives were really, of all the inconclusives in the study, really corresponded to exclusions. And so if you were to count the inconclusives as incorrect, you end up with a 66% false positive rate. That's, of course, also not correct, right? That's the other extreme. And so how should we count the inconclusives in order to come up with a more realistic error rate in terms of both false positives and false negatives? And I'm using completely arbitrary numbers there. I'm saying, well, let's suppose that 70% of those inconclusive decisions are really correct. There was no markings, or, there was no way you could go one way or the other. If 30% are incorrect, then you end up with a false positive rate of 20%. So what I'm trying to say here is that it's very difficult to estimate the actual error rate of this type of analysis because we don't really know how to do this well. So can we move away from this type of categorical conclusions into something that's a little bit more quantitative, if you will? So this is what we're going to do. So again, let me put the two propositions up there. And then as a scientist, you gather evidence. That evidence we are going to call E. For example, the evidence might be that the DNA profile from the stain at the crime scene and the suspect's DNA profile are a match, so they are the same. And then you ask yourself, does that evidence support one or the other proposition? And that's what the likelihood ratio will tell you. So the likelihood ratio, I don't know how many of you guys have sort of tried to look into this new paradigm. The likelihood ratio gives you a one-number summary, if you will, of the weight of the evidence in favor of one or the other proposition. So in the numerator, you ask yourself, what are the chances that I observe this evidence if, in fact, the two items have a common source? That's the question. In the denominator, you ask yourself, what are the chances that I would observe the evidence I just observed if, in fact, the items have a different source? So in other words, I have two scenarios. One scenario is same source, the other scenario is different source. And I ask myself, and I have the evidence that I have observed, and I ask myself, how likely am I to see this evidence if the same source scenario is true? And then how likely am I to see this evidence if the different source scenario is true? And so notice that to say something about the numerator, to come up with a value for the numerator, all you need is the crime scene data. So you need to, this is how you calculate the numerators in the likelihood ratio. But in order to say something about the denominator, you need to have some population information. And I'll give you a very simple example in the minute, because the denominator is what we would call the probability of a coincidental match. I see a match, but maybe this match occurs by chance, not because the suspect was the source, but because somebody maybe that has the same attributes as the suspect may have been the source. So here's a very simple example. Suppose you have a blood stain from a crime scene and you find that the blood stain is type B+, and the suspect, lo and behold, is also B+. And so in Brazil, about 8% of the population is B+. And so how do I calculate likelihood ratio? Well, the numerator, if I assume that there's no laboratory error, that nothing weird happened, nobody mixed the samples, then the chances that I would observe a match, if the suspect was the donor, has to be close to 1. So let's call it 1. The denominator is the probability that I would observe somebody else that would also match the crime scene stain. And because I have this population information, I know that there's another 8% of people that could have been the donors of that stain at the crime scene. So the likelihood ratio in this case is 12.5. I can actually calculate a number. And how do I interpret that number? It's very intuitive. That number is, I can say, it is 12 times more likely to observe a match if the suspect was the donor than if somebody else was the donor. That's the way you interpret that likelihood ratio. Now, notice that the likelihood ratio, of course, let's suppose now that instead of B+, the match, both the stain and the suspect were A+. And now, we still have a match, but that match is much less significant because it's much more common to find a person in Brazil that is A+ type rather than B+ type. In fact, 34% of Brazilians have blood type A+. And so the likelihood ratio now here is, again, 1. But now I divide by 0.34, which is the likelihood that any random person in the population would also match the crime scene stain. And so suddenly you get only about a 3. And so if this is your match, the best you can say is it is about 3 times more likely to observe this match if the suspect was the donor than otherwise. Okay, so that's a very simple example, but that translates into other disciplines. This is forensic DNA, and in forensic DNA analysis, this approach has been in use for decades. And so, for example, here is one particular marker, the TH01 marker, and let's suppose that at the crime scene you find a blood stain again, and now you look at that particular marker and you find that alleles at the marker are 7 and 9, and the suspect, now you look at the same marker on the suspect, and lo and behold, there's a match. The suspect is also 7 and 9. So now you ask yourself, how likely is it to observe this match at this particular allele? And so the same so now I have population values, like I had, a proportion of individuals with certain blood types. I have the same type of information for allelic frequency. So these are the possible alleles at that particular marker, and about 16% of the population has allele 7, about 20% has allele 9. So if I know something about genetics, I know that you get one chromosome from mom, one chromosome from dad. So you could get an allele 7 in one of two ways, an allele 9 in one of two ways. So to observe that combination of 7 and 9, what's the probability of that? Well, it's 2 times the frequency of 7 and the frequency of 9, and you get 0.064, which for that single marker match gives you a likelihood ratio of about 15.7. So again, it's 15, almost 16 times more likely to observe a match at this particular marker if the suspect was the donor of the blood stain than otherwise. In the DNA world, people sometimes report results in terms of random match probabilities, and that's simply 1 over the likelihood ratio. Now, in DNA, we have lots of markers, and so the same type of calculation is applied to several markers, and these markers are assumed to be inherited independently. They are in different chromosomes, for example. So if you compute each, a random match probability for a large number of markers, in order to calculate the random match probability for the entire set of markers, you simply multiply those probabilities, which is equivalent to multiplying the likelihood ratios and then taking 1 over. And so this is how you end up with gigantic likelihood ratio numbers, or bazillion, and tiny little random match probabilities. So if you end up with a likelihood ratio that's 17 million, you would say it is 17 million times more likely to observe this match across all these markers if the suspect was the source of the stain than otherwise. So why does the likelihood ratio work so well in DNA? Because there's some very important things that happen. First of all, we understand the biology pretty well. Second, we have statistical models that reflect that biology. So the models reflect nature, the biology. And third, we have population information. So with those 3 things, we have all the pieces that we need in order to calculate a likelihood ratio for DNA. Of course, there's a few assumptions in the background still, and there's still a few problems. For example, somebody needs to call the alleles and say this is 7 and this is 9, and that's a subjective process, so there might be a little issue there. We have mixtures of DNA, and the examples I've been giving were for single donor samples. Mixtures are really different animals and present different challenges. And even if you do find a match and you're pretty confident that you have the right donor, does that make the person guilty? And not necessarily, because that person could have deposited that DNA at the crime scene for perfectly valid reasons. So there's all the question that Didier mentioned briefly about understanding activity level issues. Okay, this is the same story, but now I'm trying to calculate a likelihood ratio when I'm looking at consecutively matching stria. So I have bullets. I have 2 bullets, one from a crime scene and one from a suspect. And I ask myself, and I look, and I can count how many consecutively matching stria there might be. And let's suppose that I observe 6 consecutively matching stria, and I ask myself, what's the chances of observing 6 consecutively matching stria if the same gun fired both bullets, relative to the chances of observing 6 consecutively matching stria if 2 different guns fired those bullets. So what I'm showing you there is some invented data, but there's actually some data. So this is just some data that I invented. And so in those, what I see is that if I have a bunch of pairs of bullets for which I know ground truth. Let's suppose that I have 100 pairs of bullets that I know were fired from the same gun, and 100 pairs of bullets that I know were fired from different guns, and I count the number of consecutively matching stria in those 200 pairs of bullets, maybe I get data like that. So maybe when the same gun fired the bullets, you tend to observe many more consecutively matching stria than when different guns fired the two bullets. In the middle, there's a little, the extremes are pretty clear, the middle is less clear. But if I ask myself, what's the chances of observing consecutively matching stria under both scenarios, I look at, for mated bullets, this is 12 out of 100. For non-mated bullets, this was only 1 out of 100. So I can calculate my likelihood ratio as 12 over 100 divided by 1 over 100. That gives me 12. So I can say it's 12 times more likely that the same gun fired these two bullets, given that I observed this evidence. Here I don't have a statistical model. I don't know how guns impart striations, like I know how chromosomes are inherited. I don't know what happens inside the barrel, but I do have empirical data, and so I can still say something using empirical data. It gets a whole lot more complicated when you have pattern evidence. And so here, my data is an image or a pair of images. If you think about images, these are composed of pixels, and I have tens of thousands of pixels, perhaps, in an image. These images are, at least the ones from crime scene evidence, they're horrible. They're contaminated. They have all kinds of, they're very low quality most often. And so the question is, how am I going to take two images, one that's typically horrible, and compare it to perhaps a high quality image of an item that I get in the lab? There's been a lot of push to use AI, and at CSAFE, we are as guilty as everybody else. We have a lot of research going that uses AI to answer this type of questions. But I have to say that if there's an option that is more interpretable, I will take that option. And so I won't talk about AI today. I'll talk about machine learning, but not AI. And hopefully I'll show you that we can even deal with this type of evidence. So let me start with forensic handwriting analysis. So you have two notes, and the question is, did the same person write these two notes? Again, current methods rely on examiners' expertise, and the final decision is subjective. Can we do something a little more objective? And so our goal at CSAFE was to develop methods that would allow you to quantify the similarity between two handwritten documents. And so how are we going to do this? And by the way, there's this, let's see, this is, oh yeah, well, doesn't work very well. Okay, that Handwriter is a tool, is a program that we have written. It's a tool that allows you to quantify similarity between two handwritten documents. It's completely free. If you want to play, you can download it from the CSAFE website. And if you have problems, send me an email. And so what we do is we start with scanned images of handwriting. We do some processing, as what we call skeletonizing the writing and turning gray pixels either into white or black, depending on what is more correct, and so on. And then what we do is convert the handwriting into graphs. And I'll give you an example here. So this is the word C-safe up there. And there's some pretty specific rules. The rules tell us where to put nodes. Those are those red dots over there. And this is just a very simple example. And that breaks the writing into these little structures. These are graphs. These are mathematical objects. They are characterized by the number of nodes, the number of edges between the nodes, the shape of those edges, and many other things. So once you have those little graphs, you can extract data, information, measurements. And so mostly these graphs correspond to letters, but not always. And so that, they're not expected to correspond to letters or numbers. So what we do is we say, all right, let's extract graphs from a document. And if you have a document that has maybe 100 words, you end up with perhaps 400 graphs. And all of them are a tiny wee bit different. And so none of these graphs is identical to the other. And so what we try to do is reduce the dimension of this problem by clustering these graphs. So constructing groups of graphs that are similar. And here, for example, is, this is where we decided that we were going to construct 40 different groups of graphs. The orange is what we call the exemplar. That's the graph in that particular group that is closest to all other graphs in that group. And the shadowing shows you the variability of the graphs within that group. Now, this is like a template, because now if I grab a document of yours and I extract the graphs from your document, I can take each one of your graphs and throw it into one of these buckets, the one that is most similar to this one particular graph from your document. So let's suppose that I extract 300 graphs from a document of yours. I can put the 300 graphs in the best bucket and then count how many graphs you contributed to each one of these buckets. And so that's what we call a writer's profile. And a writer's profile might look like this. So here we have 3 writers, and each one of those bars corresponds to one of those buckets, right? One of those clusters. And for example, writer 1 at the top contributed lots of graphs to bucket 1, but very few to bucket 2, and so on and so forth. The second writer contributed a ton of graphs to bucket 2, but fewer to 1, and so on. It turns out, and we have 40 of these frequencies, it turns out that these frequencies are highly informative. So if I look at the chances that 2 documents written by you have very similar frequencies, that's much higher than the chances that a document written by you and a document written by somebody else will also have similar frequencies. So the data that we use are those 40 frequencies. We also extract other information from the shape of writing, like, the slant of the writing and some other things. These are the data that we can extract from these documents. And what do we do with this data? Well, it depends. If we have an open set situation where I have a suspect and a document and I want to know, was the suspect the author or the writer of this document? That's one approach. If I have a closed set, that's a different approach. And very quickly, and Handwriter, that tool that I talked about, does all this stuff. It extracts the graphs, it puts them into buckets, you have to tell the software whether it's a closed set or an open set, but then it does everything else. And here's the open set case. You may have, that might be the writer profile for the sample 1, and that's the other profile for sample 2. And we combine all this data using pretty simple methods. In this particular case, it was a random forest that we used to combine all those frequencies, and we end up with a similarity value, which in this case was 0.3. Now, is 0.3 high, is 0.3 low? And in order for us to decide whether 0.3 is high or low, we have to have some population information. So like in the case of consecutively matching stria, we may have, for example, lots of pairs of notes, some that we know were written by the same person, some that we know were written by different people, and for each one of those pairs, we can calculate the same similarity score. And what you're seeing down there are for example, the values of the similarity scores that you tend to observe when you have different writers, those would be the yellow ones, and when you have same writers, those would be the blue ones. And so you look at the one you obtained for your particular case, and you ask yourself, is this more typical if the notes were written by different people, or if the notes were written by the same person? And so that's, in this particular case, 0.3 is much more typical of different writer than of same writer. So that allows you to, in fact, we can compute what's called a score-based likelihood ratio out of this as well. When you have a closed set, that's in a sense a little easier because you know that the writer has to be somebody in this particular set of individuals. And so the approach is a little different. We use the same data, but now we're fitting a statistical model, and that model allows us to calculate what we call the posterior probability of writership. In other words, if I have 10 writers, I can tell you what the probability that each one of those 10 writers is of being the writer of that note. And in this case, for example, I might have, writer 2 may have a chance of 0.99 of being the writer, and the other two writers have very, very small probability. So I don't know how many of you guys have heard of Flash ID. This is a big commercial software that was developed by the FBI. And we compared Flash ID to Handwriter, and that's how they both performed when you have a very small question document with only one sentence, 3 sentences, 5 sentences. So good old Handwriter does pretty well, in particular considering it's free. Okay, bullets. And I should say I am going to thank, I don't know if he's here, but Jim Hamby is here. Jim Hamby is one of the pioneers in the world of firearms in the United States, was one of the first practitioners to actually collect some data. Oh, and the data that we use was, in fact, the data that we got started with was very generously contributed by Jim, so we're very thankful for his guidance. So this is the inside of a barrel, that's a bullet. When you fire a firearm, you know what happens. There's an explosion inside the barrel. The bullet gets pushed down the barrel. The barrel has this thing called rifling, which is at an angle, and that imparts rotation to the bullet, and that makes the flight more stable. And so what firearms examiners focus on is the striations that are the result of microscopic imperfections on the inside of the barrel. And so what I'm showing you there in a rectangle is a bullet, and the area in the rectangle is called a bullet land. Most bullets, that depends on how many grooves, that depends on the rifling of the barrel, but examiners focus on those striations. And so when they make a comparison, they look at the striation on the question bullet, they look at the striations on the test shot from the suspect's gun, and they look to see how many of these striations coincide, corresponding between the two bullets. What we do is we say, all right, this is a surface, the surface of the bullet. So what we look at is we use confocal microscopy. This is very high resolution microscopy to map the surface of that bullet. Essentially, we're looking at the surface topology of this bullet. And these instruments, you see a little picture up there, gives you essentially a 3D map of the surface of that land. And so what I'm showing you at the bottom here, this is a 3D image of one bullet land. The two ends are the grooves. We focus on the land engraved area in between the grooves. And essentially the data that you get out of this is a file with x, y coordinates on the surface of the land. And for each x, y coordination at each location, you get the depth of the surface. So that tells you about the striations. And typically, so examiners will say that striations are best at the bottom, close to where the bullet breaks off. And so we have a computer, our algorithm identifies the crosscut where those striations are most stable. Meaning if you move up or you move down a little bit, the striations don't change. So what do we do with that? Well, at the top, we have the same bullet land, and then right below it, I put it sideways, so you see a little curvature. And so we take that data and we fit some statistical models. Essentially, what we do is we take those pixels, we extract the curvature because that dominates, and come up with this plot up here. That's what we call the signature of a land. And the ups and downs there simply reflect the striations in that land. The x-axis here is about 2 millimeters. That's about the length of the land. So we're talking very high resolution here. So if you have two bullets, you can extract the signature from both bullets, overlay them, and then say, align them as best you can, and then ask yourself, do these two signatures indicate that the same gun fired these two bullets or not? And so what's the next step? The next step is to take measurements, much like we did with handwriting. I'm a happy camper if somebody gives me these two signatures, because I can measure all kinds of things there. I can measure the number of peaks that are at the same locations. I can measure the number of valleys that are at the same location. I can get an estimate of the area between those two curves, or the height, the difference in the heights of the peaks, or the depths of there's any number of things you can measure. And so we've measured, so let me, I'm almost done. So we measured 7 things, 7 features, and combined them using, again, a random forest. And these are the results we got when we used one of the Hamby sets of bullets. The similarity scores that you can calculate when bullets are known to have been fired from different guns are all very low, all below 0.25. The similarity scores when you know that bullets were fired from the same gun are all very high. So in this case, there's perfect separation. Now, this is a little cheaty because I developed the algorithm and tested it on the same set of data. So what happens when we apply the algorithm outside of the sample on a completely different set of bullets? So we issued a challenge in the United States. We asked police departments to send us bullets and not to tell us whether they were matching or not matching or what have you. So at the top, we have a set that we got from the Phoenix PD. And what they did is they sent us bullets fired from 8 different barrels. And they said, here are 3 bullets that were fired from this barrel, here are 3 bullets fired from this barrel, and so on and so forth. And then they sent us 10 question bullets. And they said, can you allocate those bullets to the corresponding barrel. And so if you look at the very top one, question bullet N, we calculated the similarity scores against all of the other bullets, all the known bullets, and it so happens that the highest values we got were for when we compared N to the 3 reference shots from the first barrel. And all those similarities were very low otherwise. So we said N was fired from barrel AG or A8. And the same happened with B, and so on and so forth. And we didn't make a single mistake. In fact, for Q and Y and Z, we didn't find any matches. So we said these 3 were not fired by any of these barrels. And so we submitted the results back, and they said, you are exactly right. And the same we did with Houston. Houston also sent us, the Houston Forensic Science Center, they were even more evil because they sent us, for example, 2 question bullets that were fired from the same gun. And again, the algorithm made no mistakes. So this is very promising, I think. It's nowhere close to, oh, I'm out of time. Nowhere close to being useful in practice, but it's getting there. So how do you go from there to a likelihood ratio? Again, let's suppose that we have thousands of pairs of bullets that we know were fired from the same gun, and thousands of pairs of bullets that we know were fired from different guns. And we can calculate the similarity score for all of those pairs. So here you have that the red distribution shows the similarity scores. This is actual data for thousands of pairs of bullets, 9 millimeter, that were fired from different guns, and the green shows the scores that we got for thousands of pairs of bullets, also 9 mil, that were fired from different guns. So if I have a case, and I have a question bullet and a reference shot, and I get a similarity score of 0.35, I ask myself, is 0.35 more typical of one or the other scenario? And in this case, you can see that the chance 0.35 is more typical of the different gun scenario, but not by much. And in fact, the likelihood rate, a score-based likelihood ratio can be calculated as the height of the red distribution at 0.2 or 0.35, sorry, the height of the green distribution at 0.35 divided by the height of the red distribution of 0.35. And so I get a likelihood ratio of about 0.6, below 1, which says this evidence is not supporting the same gun proposition. This evidence is more consistent with different gun proposition. If, on the other hand, I get a score, a similarity score from my case of about 0.7, then it's pretty clear that that is a strong indication of same gun. But I won't say I identified. This is an identification. What I'm going to report is the likelihood ratio. And I'm going to say it is 2,200 times more likely to observe this similarity score if the 2 bullets were fired from the same gun than otherwise. So I am going to skip the chemometrics, but if anybody's interested, I'll be happy to talk about this. It's pretty similar. So this is my last slide. A few observations. There's a lot of data generated in forensic sciences. These data tend to be very rich, but at the same time, they can be very complex. This is not your statistics 101 data that you can analyze using standard methods. So it's a challenge. I have to emphasize the importance of understanding whatever data you're working with. Understand the data provenance. Who collected this data, under what conditions, what are the limitations? People are very happy these days to just throw data into some algorithm and get a result. That's not a good idea. Think as a statistician. It's, identify things you can actually measure and measure them, and then be mindful of variability, either within sources or between sources, and use your superpower. As a forensic scientist, you have a superpower, and that is that you understand evidence. Yeah, you know what possible sources are, you know how to carry out this analysis, and the only thing I think where the message is, please consider the two possibilities. You observe some evidence, you do the best you can to analyze this evidence. Consider the chances of observing that evidence under the two competing hypotheses. Same source, what are the chances that I observe what I observed? Different source, what are the chances that I observe what I have observed? And then see whether that evidence supports one or the other proposition. So thank you. I'm sorry for going over time. This is our website. My address is very easy. If you go to Iowa State, Alicia is my username. Feel free to write. I don't know if we have time for questions, but yeah. Thank you. Any questions? Do we have time? Sí, pero no, no questions, right? Okay. Oh, there's a question. Haha. Okay. The gentleman over there. Ah, yeah. We don't. I'm sorry. Okay, one question. I'm sorry. I should have said that in the CSAFE website, you will also find a lot of training, courses, short courses, long courses. Everything is free. All the software tools we produce are free too. And we have one that's called Bullet Analyzer. That is what I use to do all these calculations. And it's pretty well validated. But anyway, so what was the question?
Bom dia. Por favor, o programa Handwriter, ele pode ser usado para assinatura ou só frases completas? De novo? Bom dia, desculpe, meu nome é Arnaldo César. Parabéns, muito obrigado pela sua palestra. O programa Handwriter, ele pode ser usado para assinaturas pessoais ou somente para frases completas?
Okay, so right now, so the question was, can you use Handwriter on an entire sentence or an entire document, or can you separate a document into words? And right now, we don't have that capability. I mean, we know how to do it, but we haven't added it to the public version of the software. So right now, it's a document, but that's coming, or a sentence. So you would have to separate the document into words yourself first, yeah. And then input the words, yeah. Thank you. Thank you.
Nosso muito obrigado ao professor Alicia.